Welcome to this exploration of one of the most influential papers in software engineering history. In 1974, Ritchie and Ken Thompson published the UNIX Time-Sharing System in the Communications of the ACM. This paper described an operating system that would become the ancestor of Linux, macOS, Android, and countless other systems. UNIX didn't just describe an operating system. It established principles that define how we build software to this day. Let's understand this revolution. To appreciate UNIX, we need to understand what operating systems looked like in the late 1960s. IBM OS 360 was massive, complex, written by armies of programmers, infamous for its cost overruns and bugs, chronicled in Fred Brooks' The Mythical Man Month. Multics was an ambitious time-sharing system developed by MIT, Bell Labs, and GE. Innovative but complex, expensive, and slow to develop. In 1969, Bell Labs pulled out of the Multics project. This left Ken Thompson, Ritchie, and colleagues without a platform for their work. Rather than wait for bureaucratic approval for a new mainframe, Thompson decided to build something simpler on a discarded PDP-7 minicomputer. Ken Thompson had been working on a space travel game for Multics. When Bell Labs left the project, he needed somewhere to run his game. Thompson found a PDP-7 nobody was using and began writing a simple file system, then a shell, then utilities. Ritchie joined the effort. The name UNIX was a pun on Multics, one of many versus one of few, suggesting simplicity versus complexity. By 1971, UNIX was running on a PDP-11. By 1973, Ritchie had rewritten it in C, a new programming language he had developed. This made UNIX portable to other hardware. The 1974 paper introduced UNIX to the wider world. UNIX embodied a philosophy that was radical for its time. Small is beautiful. Make programs work together. Text is universal, and avoid captive user interfaces. This was the opposite of the monolithic systems of the era, where everything was integrated and interdependent. UNIX's file system was elegant in its simplicity. Everything is a file, hierarchical structure, uniform naming, and 3 access types. This design was so successful that virtually every operating system since has adopted some form of it. The paper describes how UNIX handles regular files. Files are simply sequences of bytes. No record structure, no required format. This was unusually flexible. Other systems imposed complex record structures. UNIX trusted applications to handle their own data formats. Files have no headers, no end-of-file markers, just bytes terminated by the file's length as recorded in the file system. Directories are special files containing the names and locations of other files. A directory entry is just a file name and an I number, a reference to the file's inode, which contains the actual file metadata. This indirection enables important features, hard links, renaming, and efficient directories. Here's where UNIX truly innovated. Device drivers appear as files. Want to write to a terminal? Open dev-tid and write to it. Want to read from a tape drive? Open dev-mt0 and read from it. The paper explains, special files exist for each communication line, each disk, each tape drive, and for physical core memory. This unification means programs don't need to know about device peculiarities. The same system calls, read, write, open, close, work on everything. UNIX allowed file systems to be mounted anywhere in the directory tree. A removable file system is connected to the hierarchy by the mount system call. You could mount a disk at AMNT or home or anywhere else. The mounted file system became part of the unified directory tree. This seems obvious now, but it was innovative. Other systems treated each disk as a separate, disconnected entity. UNIX processes are described simply. Image is the current state of a program's execution, and process is the execution of an image. The process model was clean. Each process has a unique identifier, user identity, and associated permissions, and processes can create child processes. 2 system calls define UNIX process creation. Fork creates an exact copy of the current process. An exec replaces the current process's program with a new program. To run a new program, you fork, then exec. The shell forks itself, creating a child. the child executes a new program, and the parent waits for the child to complete. This separation of create process from run program enables powerful features like I/O, redirection, and pipelines. The shell is UNIX's command interpreter, but it's not special. It's just a regular user program. The paper describes the shell's simplicity. When a command is typed to the shell splits into two processes, one of which carries out the command, the other waits for completion. This ordinary program nature meant anyone could write a better shell, multiple shells could coexist, and shell scripts were just programs. The paper describes a powerful innovation, I/O redirection. When the shell executes a command, the standard output of the command may be sent to a file rather than to the terminal. For example, lsFileList.txt redirects the output of ls to FileList.txt. The ls program doesn't even know it's writing to a file. Similarly, less redirects standard input from a file, like wc lsFileList.txt. The program doesn't need to know about files. The shell handles redirection. The most innovative feature, the pipe. A sequence of commands separated by vertical bars causes the shell to execute all the commands simultaneously. Output from ls flows into wc without any intermediate file, as in ls pipe wc-l. Pipes enable complex operations from simple tools, cat access dot, log pipe grep, error pipe sort pipe, UNIX dash, C pipe sort dash RN pipe head. This pipeline reads a log, filters for errors, sorts lines, counts unique occurrences, sorts by count, and shows the top results. Each program is simple. Together, they're powerful. UNIX programs designed to work in pipelines are called filters. grep, sort, wc, head/tail, sed, and awk. Each filter does one thing well. Combined through pipes, they handle complex text processing. This is the UNIX philosophy in action. Small tools working together, a revolutionary aspect. UNIX was written in C. Earlier operating systems were written in assembly language, closely tied to specific hardware. The paper notes, the entire system was recoded in C in the summer of 1973. This meant UNIX could be ported to new computers by recompiling rather than rewriting. C itself emerged from UNIX development. Dennis Ritchie created C to make UNIX development easier. The two evolved together. By writing UNIX in a high-level language, universities could study it, it could spread to new machines, others could modify it, and the ideas could be implemented elsewhere. This portability was crucial. UNIX spread through universities, then into industry, then around the world. The paper doesn't explicitly state the UNIX philosophy, but its principles are clear. Write programs that do one thing and do it well, write programs to work together, and write programs to handle text streams. Doug McElroy later summarized, "This is the UNIX philosophy. Write programs that do one thing and do it well. Write programs to work together. Write programs that handle text streams, because that is a universal interface." The paper enabled a remarkable outcome. Universities could teach from real operating system source code. Berkeley received UNIX and enhanced it, creating BSD. BSD added the TCP/IP stack, the VI editor, the C shell, and virtual memory improvements. BSD was itself open source, spawning FreeBSD, OpenBSD, NetBSD, and eventually influencing macOS. In 1991, Linus Torvalds, frustrated by licensing restrictions, wrote his own Unix-like kernel from scratch, Linux. Linux implements Unix concepts, the file system, processes, fork/exec, pipes, the shell model. The paper Ritchie and Thompson wrote described the system Torvalds re-implemented. Today, Linux powers most web servers, all Android phones, supercomputers, cloud infrastructure, and embedded systems everywhere. Apple's operating systems also descend from UNIX. Next built their system on BSD. When Apple bought Next, this became the foundation of Mac OS X. Mac OS, iOS, iPadOS, watchOS, and tvOS are all certified UNIX systems. Every iPhone runs on UNIX principles described in this 1974 paper. UNIX shaped how we write software: modularity, text as interface, scripting, portability, and open source. Many essential tools came from UNIX or its descendants: grep, make, yak/lex, vi/vim, and git. The command line interface you use today is essentially the UNIX shell, refined over 50 years. UNIX wasn't perfect. Cryptic commands, inconsistent tools, security as afterthought, and file names as strings. But these limitations were often the price of simplicity, and many have been addressed in UNIX's descendants. In 1983, Ken Thompson and Dennis Ritchie received the Turing Award for their development of generic operating systems theory, and specifically for the implementation of the UNIX operating system. The award recognized not just technical achievement, but lasting influence. The UNIX system has spread beyond all expectation. Ritchie and Thompson showed that a small team, with good ideas and elegant design, could create something more influential than armies of programmers working on complex systems. The UNIX Time-Sharing System is remarkable for several reasons: clarity, completeness, influence, and accessibility. The paper has been cited thousands of times and is still assigned in operating systems courses worldwide. The 1974 paper introduced a system that would shape computing for decades. UNIX's principles: simplicity, modularity, text streams, composable tools, became the foundation of software engineering. Its descendants run on every smartphone, power the internet, and enable cloud computing. When you use Linux, macOS, or Android, when you pipe commands together, when you write text files and shell scripts, you're using ideas from this paper. Dennis Ritchie and Ken Thompson didn't just build an operating system. They showed us how operating systems should be built, and we're still building on their foundation.